Hi, I'm Alex.
And I'm Kenny, and this is our project on very small scale localization using IR. So, with the recent research and development in IoT technology, more and more wearable and IoT devices are entering the market, and there's a stronger demand for localization schemes that work at a very small scale and work for free moving devices. So, BLE and RSSI are examples of localization schemes. BLE RSSI has about a zero point 0.5 meters position error, which is really inaccurate if we're operating at a personal level. Ultra wide bandwidth has an extremely high cost, and that's something we also want to avoid. Additionally, traditional localization schemes rely on stationary beacons, which is really bad for free moving and mobile devices. So we want to explore with using IR to develop a new localization scheme that operates in the millimeter scale with about 5 millimeters of accuracy, that can track moving bodies without the use of stationary beacons and is very low cost.
Instead of using BLE, RSSI, or ultra-wideband for localization, we decided to use beacons with IR emitters and receivers to track relative distances based on light intensity. To do this, we designed custom PCBs for a 2D use case powered by the Arduino Nano 33BLE Sense. The Arduino's BLE capabilities allow us to communicate between nodes to avoid crosstalk. One of our additional goals is to make all beacons equal, so we use dynamic selection of the peripheral and central BLE devices during this communication. Additionally, we plan to try to integrate IMU dead reckoning as a second source of location to improve our location accuracy. Our strategy to measure distances between the beacons is to blink the beacons in turn and take readings on the other beacons that are not blinking. So as you can see in these 3 steps, each of the beacons blinks in turn, and there will be a gradient in light intensity at the other 2 beacons. Our design uses 3 receivers and 1 emitter. This allows us to both calculate the distance from a receiver on one board to the emitter on the other board, and to use the distances between these receivers and the emitter to calculate the angle by using a triangle and using known distances and angles. We used a single emitter design with a reflector so that we can get a symmetric pattern of light intensity around our board. If we had decided to, instead of using a single upward-facing emitter, use multiple outward-facing emitters, we would have had higher and lower intensity regions. The goal of this design was to make everything uniform so that no matter where the beacon is around, it'll still get a uniform intensity.
So currently with our BLE network construction, we've set up each node to have the same set of code that dynamically allocates themselves as either a central or peripheral device. To walk through the algorithm, on initialization, we generate a random number, and this is a delay in order to avoid a race condition between nodes. After that, it scans the networks, trying to see if there's any existing peripheral, which is like a network master. And then, based on whether it exists or not, initialize a node as the peripheral if the peripheral is not already present, or as a central device to connect to a peripheral and listen. Whenever a peripheral device of the network disconnects, all of the nodes will run through this algorithm once more in order to reestablish the network with a new peripheral. So in terms of the physical design of our system, we've already designed the schematic, ordered all the parts, ordered the PCB, and soldered everything, and assembled everything. Along with that, we've also designed 3D printed frames for our PCBs, just to make sure that all of our nodes are constructed the same way and symmetric. And we've run a couple of tests just to characterize our circuits.
We examined 2 options for IR reflector designs. The first is cardboard covered with aluminum foil. The second is a mirror. The mirror is more ideal of a reflector, but it is more expensive, and the aluminum is cheap and easy to make, but has higher variance.
So to go more in depth with how we tested our circuits, here's a description of the testing environment and methodology. So inside of a dark room, we set up a single emitter node and receiver node and used a hand mirror as the reflector, so that way we got as close to an ideal reflector as possible, and we were testing only the IR emission and receiving. And we measured the voltage at the receiver node using an oscilloscope. So I've provided all of the details here for anyone who wants to look in depth later, But to summarize, we tested for repeatability, so making sure that on every power cycle we'll get the same results. The maximum percent difference we got was about 4.7%. In terms of distance, we took each node and placed them a measured distance apart and measured the voltage at the receiver. And with that, we plotted this exponential looking graph down below here in the bottom right. So in terms of the variance between receivers, that's making sure that the actual receiver circuit on the same PCB is matched in gain. And testing between two receivers, we got a maximum of 5.8% difference. For the symmetry around the emitter, we took the receiver node and rotated it around the emitter at an equidistant, just to make sure that the measurements stayed the same, indicating symmetry. And our maximum percent difference was about 10.5%.
In order to extend our range, we are running the IR emitters above the rated continuous current, which means we need to use pulses to avoid causing damage. In addition to this, we are using an averaging filter to reduce noise, so we take a series of readings and then average them for each individual measurement we take. This causes a synchronization problem, since now we have the value read by the receiver, which is an average of several readings, must be entirely located on a high pulse of the emitter. So as you see in this diagram, we chose to use 12 readings 1 millisecond apart to line up to the 10 millisecond pulses of the emitter. This means that we are guaranteed to have at least one of the 12 readings be entirely located in one of the high pulses. We then select the maximum reading from these 12 and use that as our reading. To fit readings on the Arduino to actual distances, we used two different calibration methods. The first method was to fit a log function using Excel and transfer this function to an Arduino function. The second technique was to use a stepwise approximation, where we take different values as thresholds and use a linear approximation in between these points. The log fit was more accurate in our tests.
So moving forward, we want to make our BLE coordination code more reliable. Along with that, we want to finish programming the IMU dead reckoning code and integrate it so that we can get a more accurate measurement of the position between nodes. Along with that, we also realized that the pillars that support our reflectors are actually very non-ideal. They block the IR and also sometimes reflect the IR. And so this changes our measurements and makes our positioning measurement very inaccurate. And then finally, we want to finalize all of our code, combine it all into a single database, and to get very detailed measurements to see how well our system meets our design goals in accuracy and flexibility.